So thank you for introducing us. So today we will talk about how we accelerate the Spark MLlib and Data Frame with our new vector processor and our middleware. So we are from Data Science Research Labs from NEC. So this is a summary of our presentation. So NEC has released new vector processor, SX-Aurora TSUBASA at 2018. And as you see in this picture, it is similar to GPGPU, but it has a different characteristics. So what is different is it has a larger memory and higher memory bandwidth. And it can use a standard program language compatible to the Xeon or other standard CPU. And previously, vector processor is just targeted for HPC. But in this new vector processor, it's evolved from HPC, and we currently are extending our target application not only to HPC, but also to the big data analytics. And we think it's this processor is especially suitable for statistical machine learning. And to show and to prove this hardware, the performance, we developed a new middleware that targeting these domains. So, and we create this middleware to get the full performance of this vector processor for using the HPC technology using C and MPI. And we also, of course, use parallelization, fully parallelize and vectorize several machine learning and data frame operation. And also, we use compatible API to Apache Spark so that it can be usable from the workloads who are using Apache Spark. And we show we can achieve the 100 times faster performance compared to the standard x86 or compatible standard Spark, now on x86. So we think today's key takeaway for this session is if you are suffering from the performance of the Spark MLlib and the data frame workloads you have, we can help to solve those kinds of issues by this hardware and our new middleware. So I think you're not so much, I'm somewhat familiar with the vector processor, but I will explain some. So it's a one implementation of the SIMD processor. It processes many elements with one instruction. And one important feature which vector processor has is it is supported by a large memory bandwidth. Since left figure shows how scalar processor works. So it gets one data from the memory and compute it in one data in scalar computation and gets a result. So its unit computation is very small, so it's suitable for the complex application who has a very complex control flow, so such as a web service servers or some kind of database transactions. On the other hand, right figure shows a vector processor. So it gets a set of the data at once from the memory and puts the register and puts the vector computation execution unit and gets a result. So it computes many elements at once, and to get the set of the data from memory, it's supported by the higher large memory bandwidth. In our vector processor, 256 elements are computed at one instruction, and the memory bandwidth is supported by has 1.2 terabytes per second for supporting those computations. So we think these kinds of the computation is suited for the simulation AI and big data that is memory intensive and requires memory bandwidth and capacity. So this slide shows our new vector processor system, SX-Aurora TSUBASA. So previously, we have developed lots of supercomputer systems. And the previous model of the supercomputer is SX-Ace. But it's targeted just the HPC, and main target customer is supercomputer centers. So we create a model for this rack type of system. But we think we have to broaden the application domain for the new vector processor And we have developed an on-card vector processor. So we downsize the supercomputer to an on-card vector processor so that we can mount on the standard x86 tower model or desktop model, or also a Rackman server. And of course, we can scale by connecting the Rackman server for HPC. So we downsize by downsizing the supercomputer to the on-card vector processor, we think we can apply the application not only to HPC, but also big data and AI. So this is a brief specification of the on-card vector processor we call vector engine. So it has a NEC designed vector processor. So its form factor is, as you see, so it's PCIe card implementation. And it has an 8-core processor, so it can execute 8 processes at once. And computation performance is 4.9 teraflops in single precision and 2.45 in double precision. And its memory bandwidth is 1.2 and memory capacity 48. And I think, as far as I know, this is the largest and fastest memory bandwidth and the largest memory capacity which has in this PCI card type accelerator. And we support startup programming interface, C, C++, and Fortran. So you can easily port the program to a vector processor. This is slide shows some more specification of the Apple processor. So its vector length is, as I said, 256 words. So 1 word is a 64-bit. So if we say the SIMD length in Intel-like scheme is, so we say 16,000 SIMD length we have. And its core is 8 and frequency is 1.6. And its core performance is 307 for double precision and 614 for single precision. And the total performance of the CPU is 2.45 and 4.91 for each for double precision and single precision. And we have 16 megabyte shared cache, and memory bandwidth is 1.2 terabyte per second, and memory capacity is 48 gigabyte. So this memory bandwidth capacity achieved by using the high bandwidth memory 2 and connecting 6 to this vector processor. So this slide shows how our vector engine executes applications. So you know GPGPU are taking a floating model. So parts of the application are executed on the GPGPU. So if you invoke the program, the application starts on the x86 side. And some of the function is written in CUDA and offloaded to the GPGPU. So in that time, you have to transfer data, and you have to invoke the command to GPGPU. And after execution at the GPGPU, result go back to the x86. So it's going back to the x86 and GPGPU. So in many cases, that kind of the communication and data transfer and control overhead happen between the PCIe, between x86 and GPGPU. In our vector engine model, we support native execution model. So whole application is, we can run whole application on VE. So of course, at first we have to invoke at the x86, but whole program are sent to the VE and start running at VE side. And whole application is executed on VE side. So what's the merits of this native model? So we think we can minimize the data control overhead and data transfer overhead through PCIe between x86 and VE. So that makes it possible to execute much easier for memory-intensive applications. So how we use it? We preparing some vector cross-compiler on the x86 host size. So we edit the program and compile it. And you can get the execution out in the x86 side. So that cross-compiler has an automatic vectorization feature and also a parallelization feature. And it supports Linux and Fortran, C++ for standard environment. And we also support OpenMP and MPI for match setting and match processing on vector processor and between vector engine cards by using the MPI. And for executing the program, we just type vexec.a10 out, and you can execute the program on the X80, not X80, our vector engine. So why vector engine? So we think compared to the other accelerator, this vector engine can accelerate memory-intensive workloads much well. So that because we have higher memory bandwidth and a larger memory capacity in the accelerator. And we support native execution model, so that minimizes control overhead or data transfer overhead through the PCIe. And we support standard programming model that will help to develop such kind of application much easier. And we support direct data transfer among multiple vector processors through PCIe and InfiniBand. So that will enable us to scale beyond the not one card. So we can scale to the multiple card to get the best performance using the multiple VEs. So why are we here? So we think Spark machine learning framework and data frame processing requiring extreme large memory can be accelerated by our vector engine. So this figure shows mapping the application and the processors which suit for the mapping the application and the processors. So X-angle shows the application which requires a computation performance. And Y-axis shows the memory performances. So as you know, the GPGPU is a very computation intensive, suits for computation intensive. And it can learn the convolutional neural network, such kind of deep learning well on that well. On the other hand, some application requires more memory performance, such like machine learning and data frame. We compare to the CPU and GPU, vector engine suits for that kind of application. And we think we can well accelerate those applications supported by Spark. And from now, we will switch to Takeo Araki, and he will present what kind of software we created.
Hi. To accelerate a Spark application using vector engine, we need to fill gap between the application and the hardware. We created a framework called Frovedis to fill the gap. And my name is Takeo Araki, and I'm the original creator of this framework. Okay, that is called Frovedis. Frovedis stands for Framework of Vectorized and Distributed Data Analytics. It is C++ framework, similar to Spark, but it supports Spark and Python interface. Using this interface, you can accelerate your Spark application using the vector engine. It is written in MPI for high-performance communication. MPI is commonly utilized in HPC field, and it is very high performance because it can utilize the hardware functionality like our DMA directory. And the framework is optimized for SX-Aurora TSUBASA, but it also works on x86 because it is just a C++ library. And it is open sourced at github.com/Frovedis. So you can try the framework and to see how it works on your x86 server or even on your laptop computer. Here's the layer diagram of the framework. In the bottom, there's a Frovedis core. It's like a Spark core. And in the middle, there's a matrix library, machine learning library, and DataFrame. On top of that, there's Spark and Python interface. I'd like to explain the framework layer by layer. First layer is Frovedis core. It provides Spark core-like functionalities like map and reduce. As I explained, it internally utilizes MPI to implement distributed processing. So it inherently supports multiple cards and multiple servers. Even though it utilizes MPI, users need not be aware of MPI to write distributed processing code. Users just need to write functions in C++ and provide the functions to the framework to run them in parallel. For example, if users want to double each element of distributed variable or distributed vector, users just need to write this function 2 times. It takes integer I and returns I times 2. And here D1 is distributed variable, just like our DD of Spark. And user just need to call map and give this function 2 times as the argument of map. Then the framework run this function in parallel and create new distributed variable R. So here's the complete sample program. It scatters a vector and double each element and then gathers. First, you need to initialize the framework by defining this variable. And here, std vector v is initialized from 1 to 8. And in this statement, the vector is scattered to create the new distributed vector, D1. It's like a C dot parallelize in the case of Spark. And this line is same as before. And here, you can gather the distributed vector to normal std vector R. As you can see, you do not have to be aware of MPI. That requires the SPMD programming style. But it looks more like a sequential program, like Spark. But it works as an MPI program. So under the hood here in the initialization, this is the definition of the variable. So constructor of this variable is called. Here, MPI init is called in the constructor and branches. At rank 0, rank means the processor number in MPI. In rank 0, returns from the constructor and execute below statements. But in the case of rank 1 to n, they wait for the RPC request from rank 0 and never returns from this constructor. And in these statements, rank 0 sends RPC request to rank 1 to n to do their work. And at the end of the function, the destructor of this variable is called. And in the destructor, finalize is called. And rank 0 sends RPC request to rank 1 to n to stop the program. Let me show you some demonstration here. OK, I'm connecting to the SX-Aurora TSUBASA server in Japan. And this program is same as the program I showed you before. I just added some output here. Because this is MPI program, to save the time, I already compiled this program. And because this is an MPI program, I need to use MPI run to run this program. So by -np, you can specify the number of processes. Here, I specify 4. And the binary name is tut. So let me execute this one. OK, so it returns the doubled this vector. And this program is actually executed on the vector engine. As you can see, it is very easy to write the program and execute the program. OK, going back to the presentation. OK, next layer is matrix library. It is implemented using Frovedis core and existing MPI libraries like scalepack pblast, laypack blast, file apac. And it supports dense and sparse matrix of various formats. Like in the case of dense matrix, row measure, column measure, block cyclic. And in the case of sparse matrix, CRS, CCS, EAL, JDS, and JDS and CRS hybrid format. This hybrid format is our original format for better vectorization. It provides basic matrix operations and linear algebra. In the case of dense matrix, it supports matrix multiplication, solving the system of linear equation, transpose, and so on. In the case of sparse matrix, it supports matrix vector multiplication. It is sometimes called SPMB, transpose, and so on. For example, if you want to multiply distributed matrix, you can just use the operator star like this. And if you want to solve AX equal B, then you can just call GSB and B. OK, next layer is machine learning library. It is implemented with Frovedis core and matrix library. It supports both dense and sparse data, but sparse data support is more important in the case of large-scale machine learning. So we emphasize the performance of the sparse data machine learning. Here are the supported algorithms. We already support many algorithms. In the case of linear model, logistic regression, multinomial logistic regression, linear support vector machine, LS for recommender system, K-means, singular value decomposition, PCA for preprocessing, word-to-vec factorization machines, decision tree, naive Bayes, and graphical algorithms like shortest path, page rank, and connected components. And we are also developing other algorithms like frequent pattern mining, spectral clustering, hierarchical clustering, latent rate allocation, deep learning, including multilayer perceptron, CNN, random forest, gradient boosting decision tree. So we will support more and more algorithms here. Next layer is DataFrame. It supports similar interface to Spark DataFrame, like select, filter, sort, join, group by aggregate. But at this moment, we don't support SQL interface. It is implemented as a distributed column store. Each column is represented as distributed vector. For example, this table is represented as these distributed columns. And this part of this column is stored in rank 0, processor number 0. This part is stored in rank 1, and so on. Each operation only scans argument columns. For example, if you want to filter this table according to the value of this column, then a filter only scans this column. And then other columns are created when necessary, according to the result of the filter. It is called late materialization, and this technique reduces size of data to access. Okay, last layer is Spark and Python interface. So far I explained the C++ API, but writing C++ program is sometimes tedious. So we created a wrapper interface to Spark. It calls the framework through the same Spark API, so users do not have to be aware of vector hardware. By using this interface, users can accelerate their Spark application using vector hardware. We implemented this by creating a server with the functionality I explained before. The server receives RPC requests from Spark and executes ML algorithm and so on, but only previous algorithm can be used from Spark because of this architecture. But other languages can also be supported by this architecture. For example, currently Python is supported. The API is cycled down. Okay? So here's how it works. Rank 0 of the Frovedis server waits for the RPC request from the driver of Spark, because the server is also MPI program. So rank 0 of the server waits for the RPC request from Spark. But data communication is done in parallel, because data in Spark is distributed among workers. So all workers of Spark and all ranks of the Frovedis server send and receive data in parallel. We assume that the data can fit in the memory of the Frovedis server. Okay, here is the programming interface. It provides same interface as the Spark's MLlib, but we need to change the importing module. For example, here is the original Spark program. In the case of logistic regression, you import some module and call logistic regression with sdd.train. In the case of Frovedis, you needed to change importing module like this and add initialize and shutdown of the server. As the argument of initialize, you need to specify the command to invoke the server, for example, npm run. But you don't have to change the here machine learning API, so you can easily utilize our hardware. Okay, so let me show you another demonstration. Okay, here I use the Zeppelin for demonstration. The application is kind of recommender system. It loads the data of movie lens and recommend the movie. And the algorithm is very simple, using singular value decomposition. And here's the normal Spark case, and here's the using Frovedis case. The content is almost the same. Okay, and the data is already loaded, so let's start the training here. I started the normal Spark case. So right-hand side, you can see the load of the x86 and vector engine. Upper side is x86, and this server has one x86 socket, and it has 12 cores, so there are 12 gauges here. At this moment, we don't use vector engine, so there's no load here. So it takes about 1 minute, so let me try vector engine in parallel. Okay, let's start. Start and end. So it only took 1.5 seconds. But in the case of Spark, it is still running. So let me check the result. I picked up a user who rated the Japanese animation highly. So here's the highly rated movies. And here are the recommended movies. So the system recommends the also Japanese animation. So the recommended system seems to be working correct. OK. And now Spark seems to end it. So it took 71 seconds, so about the 50 times faster. So let me check the result in the case of Spark. OK, this is the Spark's result. And this is Frovedis result. So the result is exactly the same. So you can get this exactly the same result with the quite less time. OK, let's go back to the presentation. OK, so far in the demonstration, I utilized the local mode of the Spark. Actually, our system supports resource allocation by YARN. It is implemented in the collaboration with Cloudera, formerly Photonworks team. It is implemented as follows. First, YARN is modified to support vector engine as a resource, like GPU. And we created a wrapper program of MPI-1, which works as an YARN client. It obtains vector engine from YARN resource manager and run MPI-1 on given vector engine here and here. And we use the wrapper as the server invocation command that can be specified at the Frovedis server.initialize. So by using this, we can seamlessly support the YARN resource allocation. OK, let's go to the performance evaluation. First one is machine learning. We utilize the Xeon Gold 6126 one socket and one vector engine with sparse data. We utilize the C++ API, and we excluded the I/O time. We used logistic regression, k-means, and singular value decomposition for evaluation. And for logistic regression, we used the click-through rate data provided by Takeo. It's about 6 gigabytes. And for k-means and singular value decomposition, we use the Wikipedia document time matrix. It's about 10 gigabytes. We use the Spark version 2.2.1. Y-axis of this graph shows the speed up compared to Spark, and Spark is 1. And blue bar shows this, the speed of Spark on x86. It's always 1. And green bar shows the performance of Frovedis on x86. And red bar shows the Frovedis on vector engine. As you can see, Frovedis on x86 shows 5 to 10 times speed up. And the Frovedis on vector engine shows the 40 to 100, over 100 times speed up. Next evaluation is DataFrame, and we evaluated using the TPCH scale factor 20. We picked up 4 queries. Q1 is group by aggregate, and Q3 is filter, join, group by, and aggregate. Query 5 is similar to query 3, but it uses a larger join, and query 6 is filter and group by and aggregate. As you can see, in this case, Frovedis on x86 shows 3 to 10 times speed up, and Frovedis on vector engine shows 10 to 47 speed up. Okay, let me switch to Hosomi-san again.
I think this performance is great, and I hope you are interested in this. So we, NEC, have opened the Vector Engine Data Acceleration Center. So NECX is the Innovation Acceleration Center for NEC's emerging technology located in Silicon Valley. So today, we have opened the VDAC lab so that several servers with multiple SX-Aurora vector engine cars running running Frovedis middleware is prepared. So we think we have a hardware and we have a software, but it's hard to evaluate for you with these kinds of the new hardware. So we prepared the remote access to this VDAC lab to evaluate our hardware and the middleware for qualified companies and universities and government labs who are interested in our hardware and the middleware. So, and we prepare some short series of tutorials on vector processing. And you can upload data to VDACs so that you can get the true sense of performance in actual application or on your data. So please request access to marketing@necx.com, or please follow at NECX for more latest news for this. So this is the last of the presentation. So NEC has released a new vector processor called SX-Aurora TSUBASA. So we think that can accelerate data analytics and machine learning applications. So we have developed a data analytics middleware called Frovedis for SX-Aurora TSUBASA. By combining these hardware and middleware, we show 10 times to 100 times performance improvement on several machine learning and data frame processing compared to Spark x86. And to try, so that you can try these kinds of performance, NECX has opened the VAC lab for accessing SX-Aurora TSUBASA AI platform with Frovedis. Thank you for coming in this session.
Thank you for the presentation. Do you work with any of the other Spark API? Would Frovedis work with any other APIs like structured streaming, or would you be able to engage with like a message broker like Kafka?
So the question is about the streaming? Okay, at this moment, we only support the kind of batch processing and
okay.
Yeah.
Just want to understand, your integration is in the backend, Tungsten, or have you modified also Catalyst to be aware of this particular vector processor?
Sorry, the question is?
In the Spark, there is two portions like Catalyst and Tungsten, the backend, right? So I was wondering where have you really integrated your MPI?
Okay, your question is if I modified Spark itself?
Yeah, did you modify Spark,
okay.
Or is it a library on top of Spark?
Yeah, actually it is just a library on top of Spark, so we didn't change the Spark.
So the Scala objects underneath that represent the RDD, they are not modified? You don't have a separate class?
Right. So we just have the separate server, and the data is sent to the server by the RPC request, so we didn't change Spark itself.
So for example, from worker 0, when you're deciding, how do you decide when to engage your server? Okay,
so here you start server by calling initialize. At this moment, some connection is established between the server and the Spark side. And this logistic regression with SDD is actually calling different function, and actually do some RPC request to the server and send the data in parallel, and after that the server shut down.
So once I call that train function, right?
Yep.
Inside the call chain, at some point you must be making the decision that instead of computing that on CPU, I have to send it to the server.
Sorry?
Right, inside the train function call, you must be making a decision like to not execute that on the CPU, rather execute that on the server.
Okay.
Actually, so how do you make the decision?
Okay, actually we changed the importing module. So by calling the modified version of logic regression with SDD, this one always calls the server side.
But of course, application developer has to decide which part should be offloaded to
Yeah.
the Frovedis or
Yeah.
should be executed on the Spark.
Yeah. So in some sense, yeah.
You have a separate implementation of, for example, logistic regression with SGD.
Yeah.
I have a question.
Yep.
So the data has to all fit in memory for the for each model. So for
Yeah.
okay, and then it doesn't matter where the data comes from, right?
Right.
HDFS
Right.
or anything.
Right.
Okay. Any other questions? Well, I had one more question. So for the benchmark, the performance, you do the x86. I guess maybe this may be a dumb question, is where does the GPU fit in here?
Okay. Actually, I couldn't find the good implementation of GPU. So because I utilize the sparse data, right? And there's no good implementation. At the time I did evaluation, there's no good implementation. For example, singular value decomposition of sparse data on GPU. So.
So you showed some query acceleration, query TPCH.
Mm-hmm.
In that, I can understand filter, you work on a data, one data frame. Things like join and those things may require you to look at many data frames, right? You got to look at other things.
Yeah.
So if you take your system and it's not integrated within the Spark, how do you actually scale it out and make sure that your acceleration works within the Spark?
So I didn't get the point of the question.
So how do you do joins across many data frames?
Okay, so it's kind of similar to what is done in Spark. We have some kind of broadcast join, hash join, such kind of things. Yes.
Sorry, one more. Would this operate like in complement to an existing on-prem HDFS system, or would this be kind of like a separate just processing engine that you then push to a persistent data warehouse or something like that?
Okay, so at this moment, this one, the server side is only the MPI program, and at this moment, the load functionality only supports POSIX file system. But actually, the file I/O is done in parallel using the MPI I/O. MPI actually supports the parallel I/O system. So, but at this moment, HDFS I/O is not directly supported. But if you want to read data from HDFS, you can, for example, read the data at the Spark side and then send to the server side.
Yeah, to answer your question, he showed the yarn management earlier, so you can add it to an existing on-prem system. So I think that's the collaboration that they did. So it's an additive thing. And if their application calls yarn for their resources, then yarn will schedule it for that piece of hardware. So it's an
Sorry, thank you.
So I have a question for these queries. Even for these queries, you have a different Python class, or how does this work? Like you have SQL integration, right?
Actually, we don't have SQL interface. Well, no, not here. Not here. So just the interface is like Spark's DataFrame. There's some DataFrame dot filter dot broadcast, something like that.
So that's your own implementation, and again, that goes directly to your server, basically. So,
Sorry.
if I'm understanding right, I mean that's your own implementation, and that directly goes to the.
Yes. Yes.
So what I'm trying to understand is, where is the integration with Spark? It seems like you can work Spark-like, but you direct your traffic to your own implementation that goes to your own servers. So it's not truly, as I'm understanding right, not truly an integration.
Actually, yeah.
Okay.
Because we wanted to utilize our own communication stack. Our framework is implemented on top of MPI. We wanted to utilize MPI because our hardware is from the HPC field. So, and we saw that MPI is much faster than existing TCP/IP-based communication stacks. So, and that's why the system is actually separated into Spark side and the server side. And I think this software architecture is not bad. The system is closely related. So Spark, we can use the, for example, latest version of Spark, even though we don't have to change our side.
So one last question. Have you looked into an integration where user does not have to do any code change, and then we install your cards in the cloud somewhere, and it just accelerates basically?
So I think that is a best case, you hope. But currently, as he explained, we create a different server for accelerating the application. So currently, you have to rewrite to the Frovedis code to get the performance. Or you have to use our API from Spark to use a vector engine.
I got that, but I'm saying that are you guys going to look into possibly doing integration?
It's a good question. So as he explained, to get a good performance with a distributed environment, we think offloading the communication to Frovedis side is very important. So it makes hard to just without no rewriting the code is hard part, we think.
Thank you.
Thanks.
Great. No other questions. Thank you all for attending. Don't forget to review the talks, and I appreciate the speakers for taking time to present to us today.
Thank you very much.
Thank you.
Thank you.